Okay, let's look at some examples for Module 4. First one, let's just talk about RMS, the root of the mean of the square. Root mean square, RMS, okay? And so we wanted to take the square root, so VRMS equals the square root of the mean of the function. So we're going to do the mean with an integral, 1 over the period times the integral over a period, say from 0 to t, or anyway, for one whole cycle. And this is a repeating waveform, right? And then we're going to take v of t squared dt. So we're going to square it, take the mean with the integral, and then take the root. So the root of the mean of the square. Okay, so for this one, we'll basically break it up into two integrals. And so it has a period of 4 milliseconds, and it has this kind of a shape. So it's got a straight line shape, and then it's got a constant, -5 kind of part. Okay, so this is VRMS is equal to this. And so let's work on this a little bit. And so VRMS is going to be the square root of 1 over t, 1 over 4 times 10 to the -3 seconds times, and let's kind of break this out a little bit, because for this integral, we're going to have two parts, like I just said. So we're going to go integral from this first part, that's a line, from 0 to 2 milliseconds, right? And what's it going to be inside there? It's going to be something, and then squared, dt, and then plus integral of this part, integral from 2 to 4, of something squared dt. All right, so let's do the easy one first. So from here to here, what is v of t? It's just -5, right? Constant, -5 volts. All right, so that's pretty easy. So it's going to be 25 squared dt, and all that is in the square root. All that is multiplied by the 1 over t on the outside there too. Okay, so what is 1 divided by 4e -3? Whoops, what's all this stuff? 1 divided by 4e -3. 250. So instead of this, let's just write 250. It'll be easier to write. Okay, let's figure out what goes inside of here, though. So we want v as a function of time. A straight line. It's supposed to be a straight line from here to here. So it's some sort of a line. Y equals mx plus b, right? The b is the y-intercept is 5, right? So b is 5. So what? And it's not x, it's a time, t, and it's voltage. So let's say v. Okay, let's just get it all into the nice. V equals mt plus b. In this case, I said b is 5 volts, so it's going to be something plus 5. And so something times time. What's multiplying time is the slope. What is the slope here? Well, we go down for this whole range. Let's just do the rise over the run here. So we're going to go down 10. So the rise is -10. And the run is 2 milliseconds. 2 times 10 to the -3 seconds. All right, so v of t in this little piece, what's going to go in here is 10 divided by 2e -3. Yes, negative of that. -5,000. -5,000 t plus 5. Okay, well, it's a function. Volts. All right, since the time is set in milliseconds, that makes our slope be a big number, but we'll deal with it. And so we'll have -5,000. Well, let's go ahead. -5,000 t plus 5, but we got to square that before we take the integral. Okay, so let's go ahead and square it, I guess. So what is -5,000 t plus 5 squared? A plus b squared is, I guess we can write out, a plus b squared is a squared, let's just go ahead, plus 2ab plus b squared, right? We just happen to have a as a negative number, but we'll deal with it as we go. Okay, so this is going to be a squared. A is -5,000 t, so 5,000 squared. Oh, wow. 25 times 10 to the 6. t squared, right, is a squared, plus 2ab, so 2 times this, so minus 25,000 t, nope, times 2, 50,000. Plus b squared, which is 5 squared, which is 25. Okay, so this is what goes in there. We're going to have to integrate that dt. Okay, so let's rewrite VRMS. Square root of 250 times, let's evaluate this integral. So integrating this, you're going to have 25 times 10 to the 6th over 3 t cubed, and minus 50 times 10 to the 3rd over 2 t squared plus 25t. All that gets evaluated from 0 to 2 milliseconds. And then for the second integral, it's just 25. Integral of 25 is 25t. 25t. Evaluated from 2 milliseconds to 4 milliseconds. Okay. So anyway, hopefully I won't run off the page. And so plugging this in, square root of 250, and we're going to have, so 25 times 10 to the 6th times 2 times 10 to the negative 3 cubed over 3. All the 0, so putting in the 2, we're going to have all these, and then we're going to subtract off the zeros. They're going to disappear, basically. So 50 times 10 to the 3rd t squared, 2 times 10 to the negative 3 squared, divided by 2, plus 25, 2 times 10 to the negative 3, 2 milliseconds. All right, all that minus, putting in 0, which is minus 0, right? And then let's just continue on here. So 25 is going to be plus 25 evaluated and times t, which t is going to be evaluated, well, let's just do it. 25 times 4 milliseconds minus 25 times 2 milliseconds. All of that gets multiplied by the 250 on the outside. All right, let's see if we can get this into the calculator. So we got square root of 250 times, in parentheses, 25e6 times 2e negative 3 to the 3rd power. And let's make sure that it all gets to the 3rd power, times 2e negative 3 to the 3rd power. Okay, oops, not outside there. Minus 50e3 times 2e negative 3 squared. And then plus 25 times 2e negative 3. That's all that. And then we get plus 25 times 4e negative 3 minus 25 times 2e negative 3. Closing off that last parenthesis. Let's see if it likes it. 5? All that for 5? Maybe so. Just a made up problem, but it could come out to be something nice. All right, so let's just check. 250, 25 10 to the 6, 0.002 cubed, 50,000, and 0.002 squared, 25 is 0.002, plus 25 times 0.004 minus 25 times 0.002. All right, yeah, so those cancel out. All right, it says it's 5. Okay, VRMS equals 5. After all that, 5 volts. Okay, so the root of the mean of the square, it's kind of like an average for an AC kind of a signal. It's obviously the average of a sine wave is just 0. So an RMS of a sine wave is not 0, but it when we square it, we think of making everything positive, and then we take the average of that and then take the square root of it. Anyway, so it gives us a one number value for the measurement of the waveform. It's kind of like a DC value for an AC circuit. Luckily, when we're doing RMS for AC, for sine waves, which is what we do a lot with AC circuits, then all we have to do, since other people have done the integrals many times, we can just say VRMS is just V peak over square root of 2. And so whatever we have 120 volts at our outlet. It's 120, actually it's 169. And so the VRMS is 169 over square root of 2. Or 170 over square root of 2. So for sine waves, so sines or cosines, we got the easy way, divide by square root of 2. For other waves, other strange shapes, we'll have to do some sort of, maybe an integral, or at least find the area under the curve kind of stuff, square it, that kind of thing to get the RMS value. Okay, so there's an RMS example. It's a commonly used way of dealing with repeating periodic kind of signals, getting a number to represent kind of the whole signal, right? Okay, let's talk about complex math. So, hopefully, I'm sure you've heard of I is the square root of -1, right? But now we're going to call it, for electrical engineers, we call it J is the square root of -1. All right, the imaginary number is J, not I, because I is current. We got too many I's already. We can't have another I. So we use J for square root of -1. Some properties of -1, or of J, if we have 1 over J, what is that going to be? It's going to be -J. If we want to, this is what we call rectangular form when we have the J's in the circuit. If we want to put it in polar form, so this would be a rectangular kind of thing. Rectangular. If we want polar, magnitude and angle. So just like when we did vectors, we had I hat and J hat. All right, so that's rectangular form. Polar is magnitude and angle. So J is 1 at an, well, this is -J, 1 at an angle -80 degrees. Or we could also say it's -90 degrees. Or we could say -1 at an angle of 90 degrees. All of these are J, or -J, I'm sorry. And so if we're plotting, we call them phasors, or complex numbers that we're going to use to deal with AC circuits. We'll have a real axis is the x-axis, imaginary axis is the y-axis. So the things that are multiplying our square root of -1, our J, go in this direction, the y direction, and things that are real, multiplying with no J in them, go in the real direction. So -J, for example, is just 1 unit down, -1 units down, and it would be a point here, or we can think of it as a vector, but it's a phasor. We call them phasors because they're representing sine waves going down 1 unit in the imaginary direction, so 1J, right? Positive J, so this is -J, which is also 1 over J, which is 1 at an angle of -90, because we've got -90 degrees here, starting at 0, -90 down. If we wanted just J itself, this would be J, right, because it's 1 high. And so J itself is also 1 at an angle of 90 degrees when we put it in polar form, right? We could say 0 plus J, because it's got 0 real part, 1 in the imaginary direction, positive in this case. Okay, so practice, do problems. Hopefully it gets to feeling better. Let's just do a little bit of an example here. Let's just say some complex number A is A plus JB, right? Real part A, imaginary part B, and let's say some other complex number is C plus JD. Okay, so these are in rectangular form. XY coordinates, rectangular square coordinates, right? So this is rectangular form. And so let's say we want to do A plus C. A plus C. Adding complex numbers. In rectangular form, adding is easy, right? It's just A plus JB plus C plus JD. There's not much to it. You're just adding the numbers. You put in their pieces. And so you can't, just like any kind of a variable expression, you can't add apples and oranges. You can't add reals to imaginaries, but you can add reals to reals. So it's going to be A plus C plus J times B plus D, right? Just factoring out the J as a coefficient. All right, so we can get the answer for adding quite easily. What if we wanted to do A times C? Well, I mean, we could do it with the FOIL method, right? A plus JB, C plus JD. Multiply it all out. I guess we can just do it. AC plus JBC plus AC plus, I just kind of did it backwards, but JBC, and then we want to do the 2 times the D, so we were going to have JAD, how we want to look at it, plus JBJD. Okay. So it looks like a whole bunch of imaginary, only one real, but what do we have here? So we've got AC plus J squared BD plus J times BC plus AD. But what is J squared? J squared is just -1. Right? So we just get, what? AC minus BD is the real part plus J times BC plus AD. But normally we don't really do it this way. Normally when we're doing multiplying of complex numbers, we would put them into polar form because it's a lot easier to do in polar form. So let's say A in polar form is some alpha at an angle of beta, and let's say C in polar form is some, C at an angle of theta. I'm running out of my Greek letters. Okay, so if we want to multiply A times C when they're in polar form, it's much easier. We just take alpha times C, take magnitudes times each other, and we add the angles, beta plus theta. All right, so if we have our complex numbers in polar form, multiplying is quite easy. So quite often we'll just take them in rectangular form, put them into polar form, and then do the multiplying. All right, especially if you have a calculator that can do it for you. Similarly, if we want to do A divided by C, we're going to do alpha over little c. But when we divide, we subtract angles. So it's going to be beta minus theta for the angle of A divided by C. Okay, so multiplying and dividing, easier in polar form. Adding and subtracting, easier in rectangular form. Okay, how do you get from one to another? Well, calculators do it well, but we can just remember, just like we did vectors with the Pythagorean theorem and triangles, we can do the same thing here, right? So we've got, say we want to convert A. We've got capital A here, and we called that, we called it alpha angle of beta, and so its real part was A and its imaginary part was B, so we've got the right triangle kind of stuff. And so if you want alpha, the magnitude of the complex number, square root of A squared plus B squared, just Pythagorean theorem. If we want to get beta, we can say tangent beta is equal to opposite over adjacent, B over A, so beta is inverse tangent B over A. If you have them in different quadrants, then you've got to watch the angles and take care of that. Let's do one in a weird angle. So let's just do a numerical example here. Let's say we have some z is equal to -3 plus j2. I don't know, make up something. All right, so we have our real and our imaginary for this complex number kind of phasor diagram kind of idea. Here we go. And so we've got -3, so 1, 2, 3, and +2, 1, 2. So The point is here. If it was a phasor, if it was a voltage or a current, we're trying to write it as a phasor, it'd be something like this, right? And so anyway, it's a complex number. And say we want to put it in polar form. All right, so we want magnitude and angle. Angle always starts at the real axis and goes to the phasor, vector phasor. All right, so this is z. Let's go ahead and do the magnitude of z first. It's the easy one, right? Square root of -3 squared plus 2 squared, right? And so square root, hello. Square root of -3, which is the same as 3 squared plus 2 squared. 3.61. All right, so z is going to be 3.61 at an angle of something, whatever theta is. So how can we get theta? Well, let's go ahead and draw the triangle over here and figure out what theta is using this triangle. And so we'll have an angle in here. Let's just call that, I don't know, call it alpha for now. All right, some angle alpha. And we can write it in terms of these two, right? Because we know z is defined by this. So this is 2 high, and then this one is 3 over. Right, so we can say, looking at this triangle, that tangent of alpha is what? Opposite over adjacent, 2 over 3. So alpha is inverse tangent of 2/3. So alpha is inverse tangent of 2 divided by 3. 33.7 degrees is alpha. Okay, but alpha is not the angle of z, because alpha is the angle in here. What is the angle of z? Theta is actually 180 minus alpha, right? Because we want this part. So this whole thing is 180. Take off alpha, so we get 180 minus 33.7. 146.3 degrees. Let's just say 146 degrees. All right, so we've got our number in polar form then that way. If we had an angle down here, we could do negative theta when we do our triangle, or if it was down like this, we got the theta in here, we could do 180 plus theta to get an angle in here. You're just going to draw your triangle with the real and imaginary parts. Find your theta, or your alpha, I guess I should call it. Your alpha in the triangle, your angle in the triangle, and then use that to get the overall angle starting from the x-axis and going around. Okay, hopefully that makes sense. Okay, and if you have your number in polar form and you want it in rectangular, it's just like the components of vectors kind of thing, right? So say we wanted, let's just say we had a number, some y is equal to 5 and an angle of 20 degrees. All right, we want it in a plus jb kind of a form. Right, so we got 5, angle of 20. So this is 5. This is 20. So we want our real part is going to be 5 cosine 20. And our imaginary part is 5 sine 20. Just like we've been doing in physics all the time, getting the components of the vectors. So it would be 5 cosine 20 plus j 5 sine 20 would be our complex number converted to rectangular form. All right. For calculators, yours may be different than mine, but let's just go ahead and show you this. Although you do need to know how to do it by hand on paper. But if we wanted to put a number in rectangular form, I could say 2 plus, and then on mine it's this pi button down here. It has an I in it somewhere. We pretend like it's a J. 5 plus I, or let's see, actually let's do the example we just did here. Let's do -3 plus J 2. I don't know if I have to put the times. Let me just try it like that way and see what it does. Okay, so it recognized it as, my mouse out there, -3 plus 2 times I. All right, but say we want it to be in polar form, so we can check this number here. Let's see. I think we need to go to the menu, and we need to do number stuff. 2, and then we need to do complex number tools. So mine is option number 9. And then, so we have these options here: convert to polar, convert to rectangular. So it's already in rectangular, so I'm going to do 6, convert to polar. And, oh, come on. Give it to me. There. All right, so it gives it to me as 3.60555, so 3.61, yay. Angle of 146.3 degrees. All right, so calculators are very handy when you're doing a whole bunch of these, but do make sure you know how to do them by hand if I would ask you that on the quiz. Know where it comes from. Okay, so that we went from rectangular to polar. If you want to go from polar to rectangular, say you had, let's do our 5, but now we need a way to say at an angle of 20 degrees. How do we enter in a polar number? Oh, I looked it up, and then let's see if I can remember. There's one of these, looks like a little book. Where is it? Can't see my calculator in there. How embarrassing. I forget how to do it when you get on camera. One of these buttons gives me a numeric. Well, I guess let's have tried. Is it this one? Is it shift and then this? No. Okay, can't find it. Oh, it is the book. It's not on the shift, sorry. This little book thing here. Okay, I think that's it. And then we gotta find the, get back. No. Oops. Let's try shift of the little book. Yes, it is shift of the little book. Okay, shift of the little book on these Inspire calculators. Anyway, somehow you got to figure out, Google on how to look up an angle, and then remember it better than I do. All right, so on mine it is control or shift, and then the little book, and it brings up all these different symbols, and it has actual looking at an angle of kind of looking symbol there. So 5 and an angle of 20. All right, if I hit enter, I think, whoops, it's mad at me because it needs to be in parentheses. Okay, let's go. Put it in parentheses. I think that's what it wants. There. Okay, so now I think it knows that as a complex number. Let me just double check. So let's go to menu and number and 9 for complex number tools, and let's convert to rectangular 7. Okay, yep. Go ahead and tell me the numbers. Oh, I didn't have the numbers before. Anyway, it did 5 cosine 20 plus 5 sine 20. Put it on there, and then you can have it. I didn't actually get the numbers out, but then so you can go from polar to rectangular that way. And if you have complex numbers in here, it can add and subtract them as complex numbers. So you could do, I think it likes them to be in parentheses, but if you do 5 plus I don't know, 6, and then multiply that by 5. Let's see if I can remember how to get at an angle of, I don't know, in parentheses first. I lost it. Oh, what happened? Didn't mean to do that. Okay, let's try it again. 5 plus I 6 and then times, and put in parentheses, let's say 25, at an angle of, shift, book thingy, enter on the angle, say 150 degrees. I don't have any idea what the answers be here. But put that in, hit enter, it does some math. We can get it to give us the numbers. If we want it in polar form, we can go to number 2, 9, and then 6, convert to polar. Hit enter. Okay, so it's 195, an angle of 160 degrees. Anyway, so calculators can do the math, the multiplying, dividing, adding, subtracting as complex numbers. You know, you could do it could be doing it as vector math. If you had 2D vectors, it's the same thing. All right, so I don't know how much you'll need this, but at least give you an idea of how you could use your calculator if you needed to with complex numbers. Okay, so let's do a little bit of an example of where these complex numbers come from, how they would be part of a circuit problem. Somewhat. Anyway, let's do a little bit of practice here. So let's say we have a voltage. V of t is, let's say it's 170 cosine 2 pi f t plus 25 degrees. I'm just making something up here. All right, so this is the sinusoidal version, the time domain version, so it's cosine. So we got a cosine wave, it's 170 tall, and it goes down to negative 170, oops, not degrees, volts. If this is voltage, this is time domain in the time. This is the this is the frequency in radians per second. F is the frequency in hertz. All right. So the period of the waveform is 1 over f. Omega equals 2 pi f. Just the normal sine kind of stuff. Okay, so if we want to translate this into a phasor domain or frequency domain, make it into a phasor. Usually the phasor is an RMS. So let's say RMS phasor. So we're going to call that capital V. So usually these are kind of cursive or script, lowercase v, v as a function of time. And when we go to phasors, we write them as kind of block capitals. And so if we call this V1, I don't know, just some V. The corresponding phasor, magnitude-wise, we've got to get the RMS from the peak, right? So the peak is 170, RMS, so VRMS, magnitude-wise, is V peak over square root of 2, like I said earlier. So we're just going to have 170, over square root of 2. Should be about 120, yeah. 120.2 volts. All right, so that's the magnitude of V. Right, we want V1 as a complex number, right? So it's going to have magnitude and angle, so 120.2. And then the angle, when it's in this nice standard form, we just read the angle. The angle is just the phase shift of the cosine from 0. So this one actually isn't, I drew it as a cosine starting at 0, but this one's actually 25 degrees shifted one way or another. And so we just put 25 degrees. Well, so this would be the phasor version of the time domain version here, all right? Time dependent V there. So notice frequency doesn't come into the phasors. When we're converting a circuit or something that has sine waves in it, they all have to have the same frequency, all right? So all of the sine waves are the same frequency. When we have a certain phasor or a bunch of phasors we're working with and complex numbers that we're working with, we're assuming that we have the same frequency. It's a one frequency circuit, basically. If it has multiple, we can do all the analysis for one frequency and then do all the analysis for the other frequency separately and bring them back together. But generally, we'll assume there's one frequency, okay? All right, and so what do we want to do with this example here? Okay, so let's say we have an impedance Z. So I assume it's in the reading, but Ohm's law used to be Ver, but now it's Viz. All right, we talked about this in physics. And so these are all complex numbers now. V and I are phasors. Z is a complex impedance. And so instead of Ver, V equals IR, now V equals IZ. everything's complex, right? So let's say we have a Z that is 500 minus J100 ohms, just like resistance is in ohms. And this is actually, the real part is the resistance of the impedance, right? Has an imaginary part though, so it's a complex number. And say we wanted to calculate I, right? So I is V over Z. Complex wise, we got 120.2 angle 25 degrees divided by 500 minus J100. All right, so now we're already going, I want my calculator to do this, right? So we can do it with calculator, or we can go ahead and do it by hand. So let's do it by hand one time at least. So for multiplying and dividing, we want polar form, right? So the V is already in polar form. We want Z in polar form. So what's the magnitude of a polar form number? Square root of the sum of the squares, right? So the magnitude is 500 squared plus negative 100 squared. But anyway, hopefully you can do the negative going out in your head. All right, what is the angle? So the angle, you got to kind of draw the picture, right? So you got positive 500 and negative 100, right? So the real part is 500. This is real. This is imaginary. And the imaginary part is negative 100. Right, so this side of the triangle is 100. So theta is here. And so theta, we can take it, so tangent theta is what? Opposite over adjacent, 100 over 500. And so theta is tan inverse of 100 over 500. No control, okay. I always want to do shift to go to trig, but I don't need shift. So tan inverse 100 divided by 500. 11.3 degrees. So theta in my figure is 11.3 degrees. In terms of complex numbers, the angle could be negative theta. So I can just use that. It could go all the way around here, do 360 minus theta to get a positive angle, or we can do negative angle. So this is negative 11.3 degrees, starting at the real axis. Okay, I like it. And so I can get my I then without doing with a calculator, with a dumb calculator that doesn't do polar to rectangular. Magnitude divided by magnitude, so 120.2 divided by this whole thing, square root of 500 squared plus 100 squared. That's not 100, we need another 0 there. Okay, 0.236. And then the angle, when we divide, we subtract angles. So 25 minus a minus 11.3 would be 25 plus 11.3, so 36.3 degrees amps. Okay, so that would be our phasor current. All right, let's see how I did and put it in my calculator. So 120. No B's needed. 120.2 at an angle of 36.3. Put that in parentheses because it likes it that way. Divided by, and let's put in parentheses, 500 plus I times, I don't think it needs a times, 100. It knows I mean times, not 1,000. I 100. Okay, so it gives it to me in rectangular form, 213.7 minus, or times 10 to the negative 3. So 0.217 plus 0.0995 J. Let's go ahead and put it in polar form. So this menu number complex 6 convert to polar. There we got it. Okay, so 236 times 10 to the negative 3, so 0.236, angle, angle of 25 degrees. Where did we go wrong? Why did I put 36.3 degrees? The angle was 25. That's where I went wrong. Let's go get that back. Let's fix it. Why didn't you guys tell me I was doing it wrong? Okay. At an angle of 25 degrees. 120.2. Angle 25 degrees divided by 500. And it's minus J100. Try that again. And then convert it to polar. 2, 9, 6. Enter. There we go. All right. 0.236, angle of 36.3 degrees. Okay. So whichever way, well, make sure you can do it by hand way, but if your calculator is good at it, you can do it that way too as a check. Okay. Polar math, complex number math is important. Okay. So let's say we wanted to know what then that current looked like as a function of time, right? We know it's going to be a sine wave or whatever. We started with cosine, so this will be we'll use that as our reference function. So we're going to bring this back as a cosine. This is RMS, right? Phasors are RMS. So if we want to get this in peak form, which is when you write out cosine in time, that's the coefficient of the cosine is the peak. And so we've got to go ahead and multiply again by the square root of 2 times 0.236, right? Because V peak is going to be square root of 2 times V RMS, or change it to I's. I peak is square root of 2 times I RMS, right? This is just a general relationship between RMS and peak values, whatever the variable is. Cosine of omega, or 2 pi f t, plus the phase angle just goes right in, 36.3 degrees. And this will be amps, all right? So I is a function of time. Just kind of write it there by inspection, or however you want to say it. Just knowing which part goes where, how to translate a phasor. Magnitude with this RMS taken care of, angle goes right inside the cosine argument. Okay? Frequency, same frequency we had at the beginning. Right? So they'll have to tell you the frequency of the source, or if it's household wiring, what's the frequency in your house, at least in the United States, F equals 60 hertz. And if you do it enough times, omega is 2 pi f is 377 radians per second. All right. 2 pi 60 is 377. Okay. What else do we want to do here? Okay, let's say we're going to add in an inductor. Add an inductor. In series. So let's say we're thinking if we had this some sort of I'm going to need more paper. So say our original circuit, we didn't really draw a circuit, but we had some Z. We said it was 500 minus J100 ohms, and we had the voltage across it. We calculated the current through it. Call it V1, I guess. So now we're going to go ahead and add in our new circuit. We're going to have our same Z, but we're going to add in an inductor. And we're going to say we have the same, I don't think we call it I1, I think we're just going to say we have the same current, but now we want to know the voltage across. So this is voltage V1, but now we want to know V2, I guess, the voltage out here with some inductor here. So inductors are L's, but their impedance, so this was Z, is still 500 minus J100. But now we're going to add in Z of the inductor. All right, to add, impedances add just like resistors. So in series, they just add up. In parallel, you do 1 over the 1 over the 1 over kind of thing. So for an inductor, the formula J is omega L, or Z is J omega L. All right. And so we need to know what is the value of L. So let's say we're adding in a 300 millihenry inductor. L equals 300 millihenries. So then Z for the inductor is J times, and let's just say it's a 60 hertz circuit. All right, so J is 377, so 60 hertz. F equals 60 hertz means omega equals 2 pi 60, which is 377 radians per second. All right, so 377 times L, which is 300 10 to the negative 3 henries. And so this comes out to be ohms. So Z is 377 times 0.3. 300, yeah, 300 times 10 to the negative 3. 300 milli is just 0.3. So we're going to get 113.1 ohms, J. All right, so our inductor has an impedance of J 113.1. And so Z total is going to just be Z, we just called this Z, plus ZL. So it's going to be 500 plus J1, not plus, minus J100. That's Z plus ZL, which is J 113.1. All right, so adding complex numbers, it's good to have them in rectangular, which they are. So Z total is, real part's the same because the inductor has no real part, but we got 113.1 minus 100, so it's going to be plus J 13.1 ohms. Okay, and so if we say we have the same current, I equals the same, which was what? 0.236, angle 36.3 degrees. Okay, so now, just like when we were doing vectors, when we're doing complex numbers, we got to get the magnitude and the angle to get the whole current, right? And so we've got that. And so we want the voltage across the whole thing. So again, we can do voltage. If we think of this as an equivalent Z, Z total is these two added together. Voltage is just going to be the current times that total impedance. So V2 is going to be I times Z total, right? 0.236, angle 36.3 times Z total, which is 500 plus J 13.1 ohms. All right. And we're wishing this was in polar form. Some calculators just do polar to rectangular and don't do the complex math. Let's go ahead and do that this time. So let's do 500 plus I 13.1. Yes, and so then we can go into the menu, complex number, or numbers, and then complex numbers, and then convert to polar, 6, enter. And so that becomes 500, an angle of 500.1.2 at an angle of 1.5 degrees. All right, and so then we can multiply. So V2 is going to be 0.236 times 500.2. And when you multiply, the angles add, so 36.3 plus 1.5 degrees. So this is a hybrid way, I guess. 0.236 times 500.2. So the magnitude of the new voltage is 118. 0.1 really. Gaining sig figs here. Probably shouldn't do that, but anyway. And then the angle is 36.3 plus 1.5, 37.8. All right, so that's our new voltage in RMS, which is actually lower than the voltage was here, which complex numbers, real with, it can do kind of odd things. But let's go ahead and see what V2 is as a function of time then. V2 is a function of time. Remember, we have to multiply by the square root of 2. 118, too many ones, times 118.1 cosine 377t plus 37.8 degrees volts, if we wanted to write it as a function of time. Let's go ahead and draw the phasors. Let's do a phasor diagram, we call it. Okay, so this is a little tricky. So the complex numbers, we don't draw the z's in a phasor diagram. We're just usually using a phasor diagram for voltages and currents, but we're doing the real and imaginary kind of idea. And so let's start off with, I've got a dog trying to help here with our work here. Hopefully she'll go away here. And so let's say we start off with V1. Yeah, let's just do V1. Let's do V1 and I first. All right, so V1 was 120 at angle 25 degrees. And V and I's aren't, they have different units, so we don't necessarily draw them to scale, but let's get their angle. So this is 45, so 25, maybe something like this. So let's say this is V1, right? 120, angle 25 degrees, volts. All right, so let's do our current. What was our current? Current is 0.236 at an angle 36 degrees. So let's just, 36 degrees is somewhere a little bit bigger, right? And let's just, 0.2 would be too hard to draw to scale, but let's just say this is I, excuse me, I is 0.236, angle 36.3 degrees. All right, so this is 36.3 degrees, and this is 25 degrees. All right, so you can see the relative angle between the two, right? Would be actually the impedance angle. But we'll talk about that later. So when we're looking at phasor diagrams like this, we think of being a little person standing here, and these things are rotating phasors. So think of these as rotating paths, and we just took a snapshot of both of them in time. And so it's the relative phase shift between the cosine and between the cosine waves that are the voltage and the current, right? That this difference in angle is the difference between the two peaks. But what we would tend to say is, in this kind of situation, when we're sitting here and watching things come by, what comes by first? If these are rotating, we think of them as rotating with a frequency omega, radians per second rotational speed, angular velocity. I comes by first, and V1 comes by a little bit later, right? And so we would say I leads V, right? Current leads the voltage in this case, right? And this is a capacitive type circuit would cause I to lead V, right? If we go to the inductor case, when we added in the inductor, we got a new V. We call it V2. V2 is right here, is 118 at an angle of 37.8 degrees. All right, so let's do V2, which is the voltage. It is in scale with this, but it's a little bit smaller and its angle is a little bit bigger. So let's say this is V2. V2, 118, angle 37.8 degrees. All right, so now the voltage V2, if we were watching them come past, right? These are all rotating in sync with each other, coming past. V2 comes past, and then I, and then V1. So we would say, usually we say what the current does with respect to the voltages we're talking about. So we would say I lags behind, or I lags. This was I lags V1. I'm sorry, I leads V1, but I lags V2. Right? Because it comes behind, I follows behind V2. Just a little bit of, I don't know, old-fashioned notation, but anyway, that's the way we talk about it with AC circuits, leading and lagging. The current leads and lags, or lags the voltage, right? In general, for capacitors, capacitive circuits, we would have I leads V. And for inductive type circuits, or with more inductors than capacitors, like this kind of thing, inductive circuit, then we would have I lags V. All right, just one note, like I was saying, the difference between these two, if we're calculating an impedance, okay, back to Ohm's law, V equals IZ. So what is Z? V over I. If we do this in complex numbers, some V at an angle of theta sub V, and some I at an angle of theta sub I, and Z has some angle theta itself. What do we get when we divide complex numbers? We divide their magnitudes, and the angles we subtract. Right, so it says the magnitude of Z is magnitude of V over magnitude of I. I could just put magnitudes everywhere here. And then the angle of V theta, or theta as of z, I'm sorry, angle, let's put a z on there. Theta z is theta v minus theta I, right? So the difference between these two, angle 1 minus angle 2, is the impedance angle, theta z. Voltage angle minus current angle, right? So if I is lagging behind V for an inductor, so for an inductor, L, inductor, theta z is greater than 0, and it's lagging, right? Current lags behind the voltage because the current angle is smaller than the voltage angle, and so theta z is positive. For a capacitor, right, theta z is less than 0 because the current is ahead of the voltage. Current angle is bigger than the voltage angle, so it's going to have theta z is negative. It's going to be the current leads the voltage. All right, I think that's enough examples for now.